We're going to sketch the graph of f of x equal 2x minus tangent x on the interval from negative pi over 2 to pi over 2 using our guidelines. The first of those being we consider the domain, and this domain is given to us as negative pi over 2 to pi over 2, and we know that tangent is undefined at places where the cosine is 0, since that's the denominator, sine x over cosine x. And that actually would be occurring at the endpoints of this interval, and this interval does not include those, so we're good for this domain. The next thing we're going to consider are any x or y-intercepts. Let's go for y-intercept first, because that's going to be easy. If we take the function and we put 0 in for x, we get 0 minus the tangent of 0, and tangent of 0 is also 0. So we've got an intercept point at 0, 0. If we're after x-intercepts, then that's one of them, 0, 0, but basically we want to figure out when this function equals 0. So that's going to be when 2x equals tangent x. Now that's not something that we can easily solve right now. We actually are going to have something that we are going to learn fairly quickly called Newton's method. And so with Newton's method we could zero in on this or find the root of this equation, or roots in this case. But for now we're just going to have to go to some technology to help us with that, and let's just do that so we can finish graphing this. And what I would do is I would think about how it was graphed, and I know that this is just a slope of 2, and I know that tangent comes along here somewhere. And so I think there's going to be a couple other places besides where they meet right here at 0. So I can grab a graphing calculator or go on the computer and get some kind of graphing thing, and I went ahead and graphed these, and I can see that there are 2 other places where these curves intersect, therefore where 2x equals tangent x. So I'm going to use technology to help me find this. So I'm going to do the second and hit the calc, and where I'm interested in is where these curves intersect, which is number 5. And there's several places and it's flashing. It wants to know the first curve, and the point I'm interested in is up here. I can see the symmetry, so once I get one, the other one's going to be the negative of that. So I'm getting it up to where this point looks like it is on the first curve, where that looks like that intersects, and let the calculator find that value. And it looks like we get about 1.1, we'll round to 2 decimal places, so about 1.17. Now there's going to be a negative one down here as well, so I'm going to have x-intercepts at plus or minus 1.17. and then of course also at 0 where my y-intercept was 0. We can then move on to our next step, which is testing for symmetry, and if we put a negative x in this function we get negative 2x, and we know a negative on tangent makes that negative. And so what we got back was the negative of the function, so this function is odd. Now that's going to help me because I can figure out when it's 0 to pi over 2, and then I can reflect that about the origin, and I will have the left half of the graph. So that's going to save me some time. So asymptotes, we know there's no vertical asymptotes because all of our values are defined in the domain. Let's think of horizontal asymptotes. So we have the limit as x approaches infinity of 2x minus tangent x. And we actually aren't going to be approaching infinity, I realized, because we are going to be approaching pi over 2, the end of our interval, because that's where we're going to stop. So let's change that to pi over 2 and see what happens. As we approach pi over 2, we can directly evaluate this one, and this will become pi. But what does the tangent do at pi over 2? And we know that goes towards infinity. And then we have a negative on here. So this one is it's basically pi minus something that's becoming larger and larger and larger. So it should get negative infinity. Now, because this has origin symmetry, then we know as we approach the other side at negative pi over 2, we're going to be going towards infinity. So limit as x approaches negative pi over 2 is going to be infinity. So since we're out of room, we'll go on to our next screen, and let's just summarize what we have so far. The domain is negative pi over 2 to pi over 2. The intercepts are 0, 0, and plus or minus 1.17 and 0. And we know that this function is odd, and so it has origin symmetry. And we know as the limit as x approaches pi over 2 of this function was negative infinity. And then of course we'll use the symmetry and get the other one. So that was steps 3 and 4. So we're on step 5, and that is to determine where this is increasing and decreasing. So we're going to look at the derivative of this function. Well, the derivative of 2x is 2 minus the derivative of tangent is secant squared x. So we are going to be interested in figuring out where this derivative is undefined or 0, and secant is 1 over cosine x, and so it would be undefined wherever cosine was 0, but cosine is 0 at pi over 2 and negative pi over 2, but not inside of the interval. So this derivative won't be undefined anywhere inside of the interval. So let's instead figure out when secant squared x equals 2. So when secant of x equal plus or minus square root of 2. Let's choose a value here, maybe like pi thirds, something that we could compute here. So if we're looking at pi thirds, and we can see since we're squaring things that once we figure that out, that's going to be the same at negative pi thirds. That's going to be 2 minus 1 over the cosine of pi thirds. So that's 2 minus 1 over, so the cosine at pi thirds is 1/2, and then that is squared. So that is 1/4, but flipped over is 4, and 2 minus 4 is negative, and negative 2, we just need to know that it's negative. So it's also going to be negative over here. So we have decreasing, increasing, and decreasing. So there's our step 5, and step 6 is to determine any local maxes or mins. Then we decreased and we increased. So here is a local minimum, here we increased and then we decreased, so here is a local maximum. So there is a minimum at negative pi fourths, and we need to put that in our function to see what that is. So let's put it in our function. Negative pi fourths in our function is going to be 2 times negative pi fourths minus the tangent at negative pi fourths. And so that's going to be negative pi over 2, and we know the tangent at negative pi fourths is negative 1, so that's going to end up making that a plus 1. So at 1 minus pi over 2. So this one was our minimum, and we're going to have a maximum at pi over 4, and let's go ahead and just change this. If this was a plus pi over 4, this would be a plus, this would be a plus, this would be minus 1, so we'd have pi over 2 minus 1. So at pi over 2 minus 1, we have a maximum. Okay, we're going to go on to the next screen. We'll keep our little sign patterns we've got here, and we'll kind of summarize what we have to give us a little more room, and then we'll be able to graph it after we do step 7, which is looking for the concavity and the inflection points. So here's our summary of steps 1 through 6 and our little pattern here of when it's positive and when it's negative for the first derivative. Now Well, so let's write down what our first derivative was so we can take a derivative of that. That was 2 minus secant squared x. So our second derivative is going to be, this is going to be 0. Here we have a power rule chain rule. So power out in front will make -2 decrease the power by 1 secant x, and then multiplied by the derivative of secant, which is secant tangent. So we can go ahead and just put a squared on this and have -2 secant squared tangent. So now what we want to do to determine, we want to determine when this equals 0 or is undefined, and again it won't be undefined with denominators of cosine x's on these. It won't be undefined on this interval. So let's figure out where it would equal 0. So it would equal 0 whenever secant squared x equals 0, or whenever tangent x equals 0. And secant squared x won't be 0. But looking at tangent, which is sine over cosine, we can see that that's going to be 0 at 0 when x equals 0. I'm going to put that down here in green. So at 0, we're going to have a second derivative equaling 0. And let's try that on either side. So if we looked at -2 secant squared x tangent x, let's consider that at pi over 4. And this is going to be squared, so this will be positive. Tangent of pi over 4 is 1 multiplied by this 2, so that tells us that that is negative. Let's try negative pi over 4. Of course, squaring this on this is still going to be positive. This tangent is going to be -1 combined with this -2. That will make that positive. So we've got concave up here, and we've got concave down here, and we've got an inflection point right here. All right, we have all the pieces, so we are ready to sketch this graph. So we'll make our axes here, and let's go ahead and make vertical asymptotes at our ends of our interval, -pi over 2 and pi over 2, because we know they are going to be going towards -infinity or infinity. Because we do have odd symmetry, we will go ahead and figure out the right half and then copy it. Let's put our intercepts on 0, 0, and 1.17. So of course there's going to be one over here at -1.17. We know we have a maximum value at pi over 4 and pi over 2 minus 1. So we're going to look like this. Because we're concave down, we are going to increase until we get to this maximum of pi over 4, and then we're going to decrease. So on the other side of this interval, we would copy with origin symmetry and do much the same. Now this should be balanced. We look a little wider over here. Here's an official graph so we can see how we did. And we didn't do too badly. We've got our correct places where we've got our concave up, then concave down, our inflection point right here, our local minimum, our local maximum.